A very good evening to you guys. I hope you like the short intro video that I have made. Now it's not a very hi-fi music video because I just composed it myself, and but it has a small short meaning behind it. Okay, and what I want to tell you is that I have put images of my lectures as well as my traveling pictures. So the motive behind it is that you should know books and lectures are important, but they can't give you the knowledge that traveling alone can give. Okay, so you should travel as much as you can, because see, the lectures or the books that you read, they give you second hand information, but when you travel you get first hand experience, and that is really awesome. Okay, so if you can afford to travel, you should travel, and in case you can afford to travel and you're not traveling, well then that's too bad. Anyway, so focusing on the lecture, so today we are going to talk about operators. Okay, and operators are a very essential part of quantum mechanics. Okay, because only when you take an operator and you apply it on a particular wave function do you get energy or any physical observable quantity of that particular quantum mechanical system. Okay, so operators are very essential, and we need to understand operators today. Now the problem is why you people do not have interest in quantum mechanics is because you mug up a lot, because you do not understand the physical significance of the mathematical terms that are written on the board, or what your teacher teaches you in the class, or anything like that. And if you do not know the physical significance of the mathematical terms that you are actually writing on your copy, you will never develop any kind of interest in that subject. Okay, because understanding the subject is the key reason why you love a subject, right? So today in this video, how is it going to be different? There are tons of videos on operators in throughout the YouTube and other places as well, but this time I'm going to tell you the physical significance of each and every term that I write on the board, and physical significance of your linear operator. What do you mean by a commutation? What is the physical significance of a commutation? Then what is a Hermitian operator? Okay, what is a Hamiltonian operator? What do you mean by orthogonal? Okay, orthogonal, you all know that two wave functions multiplied over infinity to minus infinity will give you value 0, but I am quite sure that many of you, in fact 99% of you would not know the physical significance behind what do you mean by when two wave functions are orthogonal, right? What is the physical significance of it? So in this video I'm going to talk about that, and I'm going to obviously take some questions as well when I'm discussing various operators, right? So now let's begin with operators. So let's understand what is an operator. Okay, so let's understand first what is an operator. So operator is basically anything which acts on a particular object and scrambles that particular object. Scrambles means changes that particular object. So let's say we have an operator A, okay, or let's say so any operator A, it acts on some object O to give us another object Y. Okay, for example, the square is also an operator. So if you take square of 2, which is our object, so square over here is our operator and 2 is our object, it gives us a value 4, which is another object, which is, you can say, scrambled. Okay, understood? So any operator acting on particular object to give a new object is called as a operator. It does not have to be always a new object. Okay, because if you multiply something by 1, if you multiply a particular object by 1, it will give you the object only, right? So in that particular case, 1 is also an operator. Multiplication by 1 is also operator. Okay, 1 you can call as a unit operator. So anything multiplied by 1 is also an operation, and it will give you the object back, right? So this is operator, anything acting on a particular object to give you a different object or the same object. Basically, generally it leads to some kind of change. Now, what are linear operators? Okay, so linear operators are operators which satisfy a particular condition. And what is that condition? The condition is that an operator A acting on some function f of x plus g of x. Okay, see, for those of you who are not from a mathematical background, do not worry, I am going to simplify this video as much as possible so that you are also able to understand this particular topic really well. Okay, because it's important to understand. This is where your base of quantum mechanics is going to form, right? So any operator A acting on two functions f of x and g of x should give us a value which is equal to operator A acting on f of x plus operator A acting on g of x. Okay, so in case operator A is operator A said to be linear if it acts on this two functions such that it satisfies this particular condition. Okay, now let's take again example. Let's take an example of the operator d by dx. Okay, let's take an example of an operator d by dx. Okay, I'll come to this side so that it becomes easier for you to understand. Let's take an operator d by dx, right? And let's say our so let's say our f of x is equal to x to the power 4 and our g of x is equal to sine x. Okay, let's assume this. Now let's take operator A, that is d by dx, and let it act on two functions. That is, the first function is f of x, so I'll take the brackets x to the power 4 plus sine x. So this is our left hand side, and on the right hand side we have operator A acting on f of x, so d by dx of x to the power 4 plus operator A acting on gx, that is d by dx of sine x. So this comes out to be d by dx acting on x to the power 4 and d by dx acting on sine x, right? So this comes out to be 4x cube plus derivative of sine x is cos x, and d by dx of x to the power 4 is nothing but 4x cube, right? I hope you know a basic differentiation. So we get 4x cube plus d by dx of sine x, derivative of sine x will be cos x. So you can clearly see that the right hand side is equal to the left hand side, and if the LHS is equal to RHS, that means the condition is satisfied, and that means that this operator, that is d by dx or differential operator, is actually linear operator, right? So it can act as a quantum mechanical operator. I mean, there are other conditions also for a quantum mechanical operator, that it has to be Hermitian, but d by dx is a linear operator. Okay, I'll tell you about the physical significance, but first let me discuss on non-linear operators so that things get a bit clearer for you, right? Now, what are non-linear operators? Okay, so okay, I'll just rub it off. Non-linear operators basically will not satisfy this condition. So the example that I can take is square root operator. Okay, an operator square root. Okay, so we have square root, and let's say our f of x is equal to 9 and g of x is equal to 16. Okay, so let's say f of x is equal to 9 and g of x is equal to 16. So square root of 9 plus 16, this is our left hand side, should be equal to square root of f of x, and f of x I told you is equal to 9, so root of 9 plus g of x I told you is equal to 16, so root of 16. So root of 9 plus root of 16, and this is 9 plus 16, so this is root 25, which comes out to be equal to 5, and this is nothing but 3 plus 4. Root of 9 is 3, square root of 9, and square root of 16 is 4, so this comes out to be 3 plus 4, that is 7, and this is not equal. So that means this is a non-linear operator because it does not satisfy this condition. So any operator which satisfies this particular condition is said to be linear, and any operator obviously which does not satisfy the condition is said to be non-linear, right? Okay, so now what is the physical significance of this particular topic? What is the physical significance? Well, it has a deep meaning. Okay, so there is something called as principle of superposition. There is something called as a principle of superposition, or you can simply say the superposition principle. And what does it state? that if we have any wave function, let's say psi, it can be written as a superposition of various wave functions. It could be written as a superposition of two or more wave functions. What do I mean by that is, this wave function, let's say it's a very complex wave function. Okay, it's a very complex wave function, and I do not know how to solve that wave function because it's obviously very complicated. Now I want to simplify this particular wave function. I can do it by writing it as a superposition of two or more different wave functions. So I can write it as alpha psi 1, okay, plus beta psi 2, and so on and so forth, plus gamma psi 3 and delta psi 4 up to infinity. I can write it, but I am taking only two wave functions. So I can write down this complex wave function as a linear as a combination or superposition of two wave functions, that is psi 1 and psi 2, where alpha and beta are nothing but some constant values. Okay, alpha and beta are nothing but complex constant values. You might have seen questions like c1 psi 1 plus c2 psi 2, so you can assume this as c1 plus c2 also. In case you are getting confused, you can consider this as c1 c2, because in the exams generally you will see as c1 psi 1 plus c2 psi 2, right? So this is nothing but principle of superposition, that you can write down a complex wave function as a superposition of two or more different wave functions. So for clarity I have taken only two wave functions. Now what is a basic time independent Schrodinger equation? According to that, the basic Schrodinger equation, Hamiltonian operator H, okay, I'll write it down actually over here. Your H operator acting on wave function psi is equal to energy into psi, where H is the Hamiltonian operator, which when operated on a particular wave function will give us the energy of that particular system. So we have a wave function which is associated with a system, and if we apply the Hamiltonian operator on that wave function, what we'll get is the energy of that particular system. Okay, so I'll discuss about Hamiltonian operator also, do not worry, but right now what I'm trying to explain is the physical significance of linear operators. Now let's say this wave function over here is very complex. So what I'll do is I'll write it down as a linear combination of two different wave functions, that is psi 1 and psi 2. So our Hamiltonian operator now is acting, instead of the original wave function psi, it is acting on c1 psi 1 plus c2 psi 2. Okay, now can you see some correlation between your linear operator term and your Hamiltonian operator term? What is the significance? What is the correlation? Sorry, we have A operator, we have Hamiltonian operator over here. We have one wave function plus second wave function. We have one wave function plus second wave function. And in case of quantum mechanical operator, it is actually a quantum mechanical operator has to be linear. So this is a quantum mechanical operator, so it has to be linear. That means if this operator is linear, it will satisfy this condition. Okay, and if it satisfies this condition, then this is equal to constant I can take on the left, c1 Hamiltonian operator acting on psi 1 plus c2 Hamiltonian operator acting on psi 2. Now this is huge. This simplifies stuff to a very basic level. Why? Because now what you have is c1, earlier Hamiltonian operator was acting on wave function psi. Now you have written it down as a superposition of two wave functions, but you might have thought that it will make things complicated, but because your Hamiltonian operator is linear, it is nothing but Hamiltonian operator acting on psi 1 and Hamiltonian operator acting on psi 2. And if we had 3, 4, 5, 6 different wave functions, then it would have been nothing but that Hamiltonian operator acting on the different wave functions. So this simplifies the things, because if this Hamiltonian operator was not linear, the equation would have become very complicated, because we have many different wave functions as superposition wave functions, and then things would have gone hodgepodge. Okay, and the calculations would have been tremendous. But because our Hamiltonian operator is linear, it means nothing but our Hamiltonian operator is acting on different wave functions. No matter how many wave functions we have, it's nothing but Hamiltonian operator acting on that wave function, right? So it simplifies stuff a lot, and that is why all quantum mechanical operators are actually linear. because then only this principle of superposition we can apply, because otherwise things will get very complicated. I think we will not be able to solve that particular equation if this was not the case. So because quantum mechanical operators are linear, only that is why we can utilize this principle of superposition. All right, so this is the significance, or the physical, not physical significance, this is the significance of linear operators, right? Okay, just let me take a water break, small water break. Yeah, now that we have discussed about the linear operators, now let's move on to commutators. Okay, now let's talk about commutators. Now before I move on to this topic, commutators, what I want to tell you is one postulate in quantum mechanics which is very important, and that postulate states that any physical observable quantity in classical mechanics, or all physical observable quantities in classical mechanics. Physically observable means like your momentum, your position, your angular momentum, your kinetic energy, okay, your potential energy, excuse me, all these are physically observable quantities in classical mechanics. So all the physically observable quantities in classical mechanics have a operator associated with them in quantum mechanics. Okay, what I mean by that is that let's say we have momentum P in classical mechanics, it's a physically observable quantity. So in quantum mechanics we have an operator which is associated with momentum, okay, and which is denoted by P hat. It's a small cap or hat on P, which denotes that this is a P operator, and the value of this P operator is nothing but h cross upon I dy dx, where your h cross is equal to h by 2 pi. Now some of you who might have studied might be getting confused. H cross upon I dy dx, they might have studied minus of I h cross dy dx. Okay, now what happens is, I don't like, these two are the same things. You can write it as this way or as this way, but I do not like the negative sign, so I do not generally write it this way. I prefer to write it this way, right? So this is your momentum operator. Similarly, you can have kinetic energy operator as well, and you can have position operator. Position operator is nothing but multiplication by x. Okay, so this you have to actually mug up, because this thing nobody actually it's very mathematical, and I don't think that knowing this is possible for you, that how we got these operators, so you have to mug it up. Okay, so it's only basic things, like you have to remember the momentum operator, you have to remember the position operator, which is nothing but multiplication by x. So you don't have to remember anything as such, right? Okay, and what is the kinetic energy operator? Kinetic energy operator is nothing but, if you take the classical mechanics, your kinetic energy is equal to p square by 2m, right? So what you do is, instead of taking p square, you take p operator square. Okay, so your kinetic energy operator will be nothing but p operator square upon 2m. Okay, and if you put this value, replace this value, this comes out to be h cross square upon I square 2m d square by dx square, d square by dx square, right? Yeah. So this comes out to be minus of h cross square upon 2m d square by dx square. So this is the value of your kinetic energy operator. Okay, this is the value of your kinetic energy operator. So it's nothing complicated, but you have to understand. There's no understanding part in this. You have to memorize this, and it's not very difficult to memorize. So all the physically observable quantities in classical mechanics have a operator associated with them in quantum mechanics that you have to remember, right? Like your Hamiltonian operator, H operator, is nothing but your energy operator. So if this operator acts on a particular wave function of a system, it will give the energy of that system. And what is the Hamiltonian operator equal to? It is the sum of your kinetic energy operator and your potential energy operator. Okay, so it is the sum of your kinetic energy operator and your potential energy operator. So this is basically one postulate that you have to remember before you move on to commutators. Okay, all right. So now what exactly is commutation and how do we symbolize it? So okay, let's say we have momentum P, and one more thing that I forgot to tell you is that we are writing momentum operator as I h cross by I d by dx, right? So this means that the momentum operator is in x direction because I am writing it d by dx. Otherwise I would have written it as d by dx, d by dy, d by dz. So it's understood that right now I'm talking about only one dimension, that is in x dimension, right? So that's why I'm writing it as d by dx. Otherwise, if I'm talking about the y dimension, then I'll say it as d by dy, or if z, then d by z, d by dz, right? Okay. I don't know what's happening. Like maybe once I start speaking a lot, in the end I'm not able to pronounce the words properly. I don't know what the problem is. Maybe I'm speaking too fast or I'm not breathing. But something is wrong. But anyway, okay, so commutators. So let's say we have P and X, okay, and we have P operator and X operator, and we have X operator and P operator, which are acting on some function, let's say f of x, right? So we have P operator, X operator acting on function of f of x. I'll write it down in brackets like this. Okay. So we want to see whether changing the interchanging the positions of the operator, does it make a difference to what value we get. So let's check that. Let's check that out. X operator, I told you, is nothing but multiplication by x. Okay. So we have P operator into x of f of x. Okay, P operator acting on x into f of x, and this is equal, and here what we will get, x operator. Now what is the P operator equal to? H cross by I d by dx of f of x. So what is this equal to? That d by dx is acting on f of x, and if d by dx acts on f of x, we will get the we'll get the derivative of that function. So x operator, we can take the constant outside, h cross by I, x operator into f dash x. F dash x represents the derivative of function f of x, and over here what do we get? H cross by I d by dx acting on function x into f of x. Okay, so now we have d by dx acting on x into f of x. So according to the product rule in differentiation, this comes out to be h cross by I. Okay, d by dx first acts on x to give us value f of x plus x f dash x. This is the value we get. Okay, this is the value that we are going to get on the left hand side. On the right hand side we are getting this value, h cross I x dash f of x. So you can clearly see that these values are not equal. This value and this value are not equal. Okay, these two values are not equal. And what is the difference? If so, these two terms are not equal, and if we subtract them, then this term and h cross I gets cancelled and this term gets cancelled. Okay, these two terms get cancelled, and what we are left with is h cross I upon f of x. So the value of this subtraction, just solve it, you'll get the answer. Okay, so the value of this subtraction comes out to be h cross I. If we subtract these two terms, h cross I upon f of x. So we get the function back, and this is the value that we are getting, and this is known as the value of the commutator of position and momentum. Okay, so this can be written as p x operator in square brackets. So this is the symbol for commutator. The symbol for commutator is whatever operator you have written down over here, p operator, x operator and square brackets. This is nothing but equal to p operator, x operator acting on some function minus x operator, p operator. So this p operator comma x operator in square brackets is your commutator, or is a symbol for commutator, and p operator, and this is equal to p operator x operator minus of x operator p operator. And to solve the value of commutator, it's essential that you take a function. Okay, you have to take a function in order to arrive at the value. So let's say we take the function psi. So p operator x operator acting on psi minus of x operator p operator acting on psi, and whatever value we get, that value is known as the value of the commutator. Okay, now if this value comes out to be equal to 0, in this case it does not, for position and momentum the value does not come out to be 0. And what you need to understand is basically this x operator is acting on the wave function. So the operator adjacent to the wave function will act first, that is immediately to the left will act first, and then over here your momentum operator will act on the wave function, and over here your position operator will first act on the wave function, right? Interchanging the sequences of the operators that are acting on the wave function. And in this case the value does not come out to be 0, it comes out to be h cross by I. And what does it signify? It signifies that your position and your momentum are not compatible with each other. So in case if you take any two operators and you operate them, okay, you take a wave function and you take out the commutator value and it does not come out to be 0, it comes out to be some value, then it says that the two operators are incompatible, or to say in a scientific way that the two operators the values of the two operators cannot be determined simultaneously. Okay, the value of the two operators cannot be determined simultaneously. That is what is the meaning of commutation, and this is actually the proof of your Heisenberg's uncertainty principle, because it says that your position and momentum cannot be determined simultaneously. So this is a very beautiful mathematical term with the help of which you can find out whether two operators, the value of two operators can be found out simultaneously or not. The value of two quantities can be found out at the same time or not, right? Not the operators, the value of the two quantities. So this position operator symbolizes the momentum, the position operators symbolizes the position, and the momentum operator symbolizes the momentum. Similarly, you can check for other operators as well. For example, you can check for kinetic energy operator and momentum operator, and for kinetic energy operator and let's say position operator. So you will know whether kinetic energy and position commute or not, and if they commute, that means you can find out both the values simultaneously, and in case they do not commute, that means you cannot find the values of kinetic energy and position simultaneously. It's actually a very good way by which you can predict whether the values of two possible quantities can be determined simultaneously or not, right? Okay, so now let's take a few examples. So this was again the physical significance of commutation, right? So if the commutator comes out to be 0, that means the two values or the two operators for which you took out the commutation, they are compatible with each other, or you can find out their values simultaneously. And in case they do not come out to be 0, then they are incompatible and you cannot find their values simultaneously, right? Okay, so now let's take example of few operators and let's see whether they commute or not, so that you also have a practice. Okay, let's take two operators, x and d by dx. X and d by dx. So pause this video and solve it and tell me whether they commute or not, right? Okay, so I hope you solved it. Now let's solve let me solve this and see whether it's commuting or not, though I think it will not commute. Okay, so x, let's take some function f of x. So operators do not have any meaning until and unless you take a wave function. So we'll take a wave function, let's say. So sorry, this is operator, x operator. So let's say f of x, we'll take f of x, or we can take psi, anything that you want. So x operator, so this is basically equal to x operator d by dx, and we are taking some function f of x. So x operator d by dx f of x plus x operator plus d by dx, sorry, minus over here, this is minus of d by dx f of x plus your minus d by dx into x operator f of x. So if you solve this value, this is basically x d f of x upon dx, right? This you can just write it down as f dash x. So derivative of f of d by dx of f of x is derivative of f of x, that you can write down as f dash x. F dash x represents the derivative of f of x, right? Minus d by dx of x into f of x. So this comes out to be x f dash x minus d by dx of x f of x. So first we take derivative of x and take the second function as it is. So derivative of x is 1. So minus of, I'll take brackets, f of x plus, now we'll take the derivative of second function, which is f dash x, and this number will remain as it is, that is x into f dash x. So if we solve this, this term and this term gets cancelled, and our value comes out to be equal to minus of f of x. So that means this value comes out to be minus 1, you can say, into f of x. So the value of commutator of x dash and d by dx is equal to minus 1. So this is the value, because this is the function that you have taken, so you can ignore this. So the value comes out to be minus 1, and these kind of questions are asked in the exam. Okay, so they'll give you 4 options. What is the value of the commutator of position operator and d by dx, or they can give you momentum operator and position operator, or they can give you kinetic energy operator and position operator, or kinetic energy operator and momentum operator. So these kind of questions are asked in the exam. In fact, this was asked in the exam, that's why I've taken this question, right? So this video has been quite long, and I've discussed your linear operators, their physical significance, and your commutators, what is the physical significance, and a few practice questions, a couple of practice questions from commutators. So I have feedback from you. This has been a very detailed explanation of the subject, right? So in case you're liking it and you are developing some interest, then I'll continue with this detailed explanation. In case you feel that it's getting too much, like, because see, these two are small topics, but I have taken out 30 minutes. So in case you feel that this is getting very lengthy, then obviously I will shorten the time. But I want you guys to develop some interest, and that is why I'm taking so much efforts in each and every topic, so that it develops some interest to understand the physical significance behind those mathematical terms. Because with guarantee that only when you understand the physical significance behind these terms, then you'll develop an interest in quantum mechanics, and even a 1 hour or 1.5 hour long video related to quantum mechanics will not bother you, right? If you like this video, please give it a big thumbs up, and do subscribe to my channel, because I put in a lot of effort. And if you subscribe to my channel, if you like my video, it motivates me, it shows me that my efforts are not going futile, they are actually being appreciated, and who doesn't like to be appreciated, right? So please subscribe. Thank you so much, and thanks for watching.